In this video, we're going to talk about a process called rationalization for rational expressions that contain radicals. But before we get into that process, we first need to make sure we're all on the same page with some language. First of all, the idea of what a rational number is and what an irrational number is. Now, with rational numbers, we often say that a rational number is any number that can be expressed as a fraction, but that's not always clear what's meant. So first of all, that includes whole numbers, so that's 0, 1, 2, 3, 4, and so on, because any of those numbers could be put over 1 and therefore expressed as a fraction. It also includes integers. Now, integers are all your whole numbers, and then also their negative cousins. So -1, -2, -3. Again, we can just make them fractions by making their denominator a 1. Of course, it includes all fractions, because fractions can be expressed as fractions. And then lastly, the group that isn't always remembered that they're rational numbers is any repeating decimal can be expressed as a fraction. So, for example, one of them that's common that we tend to remember is 1/3 is the repeating decimal 0.333 with 3 repeating forever. So obviously that can be expressed as a fraction as 1/3. Any of those repeating decimals can be converted to a fraction. So then for irrational numbers, the way we sum up what an irrational number is that it's a non-repeating, non-terminating decimal. So non-repeating, non-terminating decimal. Now, by their very nature, we can't write this out because we can't write something that goes on forever. With repeating decimals, we at least have a notation to say, hey, this is going to keep repeating. But if we put them in decimal forms, irrational numbers, we can just express as an approximation by rounding them off. So usually when we write irrational numbers, we have a symbolic way of saying them. So probably the most well-known irrational number is pi, which we oftentimes estimate as 3.14, but that again is a decimal approximation. You can't actually write out pi because it goes on forever without repeating. For the purposes of what we're covering in this video, another type of irrational number is something like the square root of 2. Now, if you take the square root of 2 on your calculator, it's going to give you a decimal result, assuming how your calculator is set up. That decimal that comes out as the square root of 2 isn't actually the square root of 2. It's a rounded off approximation because the square root of 2 is an irrational number that will go on forever and ever and ever. So really, any of our radicals that we cannot simplify into a perfect whole number or an integer or a fraction, where there's stuff left under the radical that can't be square rooted or cube rooted or fourth rooted perfectly, those are going to be irrational numbers. So, for example, the square root of 4 can be simplified perfectly to 2, so it's a rational number. Whereas the cube root of 5 cannot be simplified. It can just be approximated as a decimal, so it is a irrational number. And these are the ones that we're actually concerned about in this idea of rationalization usually, is dealing with an irrational number and converting it through proper mathematical techniques into a rational number. So I'm calling that rationalization. There's two ways that we see this. I'm going to clear out the screen so we can talk about that. So let's say we have 3 divided by the square root of 2. Sometimes it is advantageous to have it so that your denominator is a rational number. So we'll go through this rationalizing process to rationalize the denominator. Or let's say you have something like the square root of 5 over 6. Sometimes it's advantageous to have the numerator as a rational number, in which case we will go through a process where we transform the numerator into a rational number, therefore rationalizing the numerator. But here's the interesting side effect of that, because we can get away with a lot in math, but there's consequences to it. So when I rationalize the denominator, I am going to cause the numerator to have an irrational number in it. And when I rationalize the numerator, it's going to flip around, and now I'm going to have an irrational number in the denominator. That's just a consequence of the process. The reason for wanting to do this is various and is addressed in higher level mathematics. For today, we're just learning the technique so that we can apply it to other things down the road. So I always like starting out by talking about what we think about as a rational number. So you understand that the goal, so if I'm trying to rationalize the denominator, in the end, my denominator should have a rational number in it. If I go through the whole process and in the end, my denominator still has an unsimplified radical in it, I've missed the whole point. So it's just important to keep that goal in mind so you know if you've at least achieved it. Even if it's somewhat achieved incorrectly, you've at least rationalized the denominator. I don't know, it's probably bad if it's achieved incorrectly as well, but it's at least indicating that you know what your goal is. Alright, now let's jump into an example so we can kind of work on the process just to see how it works. So our directions are to rationalize the denominator, and I have 5 over the cube root of 9. So again, the goal of rationalizing the denominator is to get it so the denominator doesn't have the radical in it, but the consequence of that is that the numerator will end up with a radical. And the technique that we're going to use for this is something we've kind of talked about before, is really with a fraction, I can introduce new material as long as I introduce it to the numerator and denominator. This isn't what I want to do to rationalize the denominator, but just for the sake of reminders, I can multiply the top by y as long as I also multiply the bottom by y, because what I'm essentially doing is unsimplifying the fraction. But whatever I introduce needs to be able to be canceled back out so that I haven't changed the value of the fraction. I'm just changing its appearance for the sake of me getting what I want out of it. So that's kind of the idea, is we're going to do something to the bottom to get what we want, but the consequence is that we have to also match that in the numerator. Now here with the cube root of 9, if I factor 9 down, that's 3 times 3. So I have 2 3's. If I had one more 3, I could cube root it, because the cube root undoes triplets. So what I want to do is multiply my denominator by the cube root of 3. If I multiply in one more cube root of 3, then that will give me 3 cube roots of 3. But whatever I do in the denominator, I have to do the exact same thing in the numerator. So when I work this out here, in the top I'm going to have 5 cube roots of 3. In the bottom, I'm going to have the cube root of, you could write that as a 27, but to emphasize what we're doing, I'm going to write it as 3 to the third. So you can see what I've done is create a triplet that now the cube root will simplify. So then when I simplify that, I get the cube root, 5 cube roots of 3 on top, over 3. So now I have a cube root in the numerator, but I no longer have it in the denominator, which achieves my objective. It's important with these problems when we start rationalizing the denominator that you do not think of this process as simplifying, because sometimes through the process of rationalization it gets more complicated. The goal isn't to simplify the problem, the goal is to get the radical out of the denominator, or if we're rationalizing the numerator, the goal is to get the radical out of the numerator. And then you just deal with the consequences. Alright, so let's switch gears and talk about rationalizing the numerator. With this example here, I have the fourth root of 5 divided by 6. So we want to get it so that in the numerator we have a radical that will simplify. Well, 5 doesn't break down, so right now we have 1 5. In order for a fourth root to simplify, we need 4 of them. That means we need 4 more 5's. So I need to multiply the top by the fourth root, we need 3 more 5's, so I need to multiply it by the fourth root of 5 to the third, because then I would get up to my 4 5's that I need. It's kind of like Go Fish. I'm asking for more cards so I can get the full hand. But whatever I do in the top, I have to do in the bottom. Alright, and then once I decide what to do, I just write out my consequences of it. So in the top, I have the fourth root of 5 to the fourth. In the bottom, I have 6 times the fourth root of 5 to the third, which is 125. I'm going to go ahead and calculate that out because it's not going to simplify. I left it in exponent form in the top to emphasize how it'll simplify. So in the top, that simplifies to a 5, and I'm left with 6 times the fourth root of 125 in the denominator. So again, it's not necessarily prettier than what I started with, but my goal was to rationalize the numerator. Now I have a 5 in the numerator, which is a rational number, so I've accomplished my objective. Go ahead and give some of these a try and see how you fare.